Hi, this is Brad Linseth. I'm with the University of Colorado in Boulder, Colorado, and I'm working on a 449 megahertz 1.2 kilowatt amplifier based on the NXP BLF578 device. I'm working on this device as part of an amplifier for a wind profiler radar for the National Center for Atmospheric Research. So I'm going to show you the amplifier in action now. So to start with, I'm running the amplifier 50 volts drain voltage, 1.3 volts for the gate bias voltage. Here's a picture of the amplifier here. It's a push-pull configuration, and I have balance on the input and the output to split the RF between both devices, and accomplish also the part of the matching circuit. I have a current probe hooked up to measure the current, the peak current, and then my input drive is these amplifiers are providing the input drive, and then the output is run into this dummy load, and then it's split three ways between spectrum analyzer and an output power meter. This has all been calibrated, and I can monitor the power added efficiency in LabVIEW, along with the gain and also the output power. This is accomplished with 2 peak power meters for input and output power. You can also look at the output spectrum with the spectrum analyzer, and then the oscilloscope shows the current probe waveform, which is run, the amplitude is measured and run into LabVIEW over at the computer side. I'm also showing the detector output from the peak power meters here. And my signal source is the signal generator here. The signal source is this generator, which is generating the 449 megahertz with a 10% duty cycle pulse of 5 microseconds. And you can see the length of the pulse here. And let's see, it's actually, I think it's actually set to 8 microseconds right now. So we'll go ahead and ramp up the output power here. Ramp up the input power, sorry. Okay, so we're seeing right now the input power is 34.6 dBm, and we're at 12% PAE, 13 dB gain. The gain is limited right now because my input match is not optimum. I need to tune that. But we are seeing an output power of about 57 watts at this level. So I'll turn the input power up, input source generator up a couple dB. Now we're up to 200 watts out, 22% PAE, and 14.3 dB gain. The current draw is 1.4 amps. That's the average current draw. Here's the peak current shown by the current probe. So we're outputting 200 watts. Go up another dB. Now we're outputting 330 watts, 14.7 dB, 29% PAE. Up another dB. Now we're outputting 527 watts, 32% PAE, 14.8 dB gain. Current consumption is 2.2 amps average. I have to adjust the oscilloscope so that way it can detect the peak current waveform. Still at 525 watts out. I up the input another dB, and I'm adjusting the current waveform settings on the oscilloscope. Now we're at 770 watts out. (14.7 dB gain, 43.6% PAE). The heatsink is starting to warm up a little bit. Take a look. I have a thermal imager here. You can look at the you can look at some of the temperatures on the device. One of the things that heats up is the output capacitors. Looks like the output caps are heating up to about 69 Celsius. I like to monitor the flange temperature of the transistor. Looks like the flange temperature is up to 72 Celsius. Go up another dB. Now we're at 45 dB in, 963 watts out, 50% PAE, 14.3 dB gain. Let's see if we can get up to a kilowatt. Getting pretty close. A couple more tenths of a dB. Now we're at 49% PAE, 1.0 kilowatts, 14.25 dB gain. DC current is 3 amps, 3.1 amps. Gate voltage 1.3 volts. Here's our current waveform. The waveform has a ringing to it because there's still a capacitor between the drain and the current probe. Heatsink is warming up. It's probably about 100 watts average there. Transistor flange is indicated at 76 degrees Celsius. Could be a little warmer than that even. So that demonstrates 1 1 kilowatt output power, and 14.2%, 14.2 dB gain, 50% PAE. Thank you for watching my presentation.